Hi, my name is Bram Kusters, and I'll be presenting to you our results on route reconstruction from traffic flow via representative trajectories. This is joint work with Wouter, Bettina, and Kevin. So our results concern understanding mobility patterns. So suppose I have this city here, and I am interested in the major traffic flows through this road network. So where people went through this city. And why would we want to know this? Well, we, for instance, can predict the effects of road constructions. We can guide public transport construction, and then there are myriad other possibilities for using this data. And we're particularly interested in origin, destination, and the routes essentially that people took through the network. So how do we get these patterns? Well, we can use several data sources to get to these patterns. For instance, we have checkpoint data, which essentially measures at fixed points in our road network how much traffic went through that point. In addition, we have GPS traces, where in essence we measure for a specific person or vehicle where it was at fixed points in time. And then there are many other data sources available. And what they have in common is that they are incomplete. So for instance, looking at the checkpoint data, we don't exactly know which route people took when going from one detector to the other. And for the GPS traces, we only have a subsample of the total traffic through the network. So a natural question that may arise is, how can we enrich data by combining data sources? And as you might imagine, what we'll be focusing on today is combining the checkpoint data and GPS trajectories, where our goal here is to reconstruct realistic routes that explain checkpoint data. And by to give you an intuition of what we mean with realistic, so we want somehow the routes that we are going to reconstruct to be present in our GPS data. So if I have this trajectory, then it might stand to reason that I want to reconstruct routes that align with my checkpoint data and approximately follow this input trajectory. So to give you more of an overview of the problem, so we are given checkpoint data, and we will assume for now that it's given as a flow field, which essentially is a assignment of positive reals to each edge in our road network, where the positive real simply means how much traffic went through this edge. And then in addition, we are given representative trajectories, some realism parameter, and we are going to do something with this data, and we want to output then weighted routes where the weights is the amount of traffic that went over this route. So looking at the realism, what we are going to assume is that our GPS trajectories are representative for the traffic in the road network. And then a realistic route becomes a reconstructed route that is geometrically similar to a trajectory in our inputs. And by geometrically similar, we're going to assume that our Fréchet distance between the reconstructed route and the trajectory in our data set is at most some realism parameter epsilon. So now that we've covered that, let's look at what we expect from our weighted routes. So we want them to explain the checkpoint data. And how do we quantify this? Well, we're going to compare the flow field that defines this checkpoint data to a reconstructed flow field from our weighted routes. So I have my flow field here with the amount of traffic on them is defined by the colors. And now I have some reconstructed routes, and they also have the amount of traffic that went over this route. I can simply sum this to my edges in the road network, and now I can compare them. And what we want is to minimize deviation between these two fields, which we'll quantify as the sum of the square differences of the amount of flow or the amount of traffic per edge. So now the big question is, what are we going to do here in the middle? And it's maybe good to mention here that a lot of variants around our problem are hard. So we'll be looking at heuristics. In particular, what we're going to do is the following. So we are going to use our flow field as a residual flow field initially. And this is in essence the amount of unexplained flow or unexplained traffic in our network. So we are going to feed this along with our representative trajectories and a realism parameter into a modified Fréchet map matcher. And this will give us realistic routes that are within the correct Fréchet distance of a representative. And in addition, here our heuristics come into play to get routes that potentially explain a lot of flow. And for more details, I'd refer you to our paper. So we combine this residual flow now with the realistic routes, and we apply non-negative least squares to get to our weighted routes. Now with these routes, we can update our residual flow field and then repeat this whole process. And then after a fixed number of iterations, we simply output our weighted routes. So to see how well this works, we are going to look at some applications. In particular, we have some experiments with a ground truth, and then we look at a real-world use case. And to compare our approach to some other baseline approaches, we propose two baseline approaches, namely one based on global min cost flow that essentially is much less constrained when it comes to this realism, namely simply select some sources sinks around our trajectory start and end, and we feed this in a min cost flow algorithm, which gives us a flow, and we can then decompose this into weighted routes. And the slightly more constrained variant is the multi-commodity min cost flow approach, which essentially allows routes in a subgraph that's within epsilon Euclidean distance of some representative. And we feed this again in a min cost flow algorithm, get a flow, and decompose this into routes. So we're going to measure our performance using the following measures. So first of all, the deviation, which is simply how well do we explain the checkpoint data. Then the realism, which says something of how close we are to our representatives. And then the cardinality and the running time of our reconstructed routes. So looking at the ground truth experiment first. So I show here a scatter plot of the realism for each route in our reconstructed route sets, and then for the different approaches. And what we can see clearly is that the less constrained versions indeed do not exactly follow the limit of the amount of realism that is allowed. So you'd expect at most a realism of 100 meters, and this is clearly not the case here. And so looking at deviation, we see that actually the least constrained approach here, so the global min cost flow, actually performs best, since obviously it has a lot of leeway to actually fully, or as close as possible, cover the flow in a road network. Looking at cardinality, however, our approach has a low amount of routes, which makes it easier to handle in any next steps in case you want to use these routes for some further analysis. And the running time is somewhat similar, although the multi-commodity min cost flow approach is fastest in this particular case. So to further analyze what exactly is going on here, we're going to look at a restricted version where we essentially only look at all the routes that are within the realism parameter. So in this particular case, at most a Fréchet distance of 100 meters. And what we see now is that both the min cost flow approaches are strongly pruned and are fairly small in size again, and their deviation is not as good as it was before. So there's a lot of not necessarily interesting routes in the previous solution sets. What we do see is that if we recompute the coefficients for instance, the multi-commodity min cost flow, then it gets a deviation of something similar to our proposed method. The only thing now is that this requires extra steps to actually get there. So it's way less efficient than our proposed method is. So then, looking at the real-world use case. So we have this road network, and these dots represent our loop detectors or checkpoint data, and the redness shows how much traffic went through them. And looking at our results, what we see clearly is that long trajectories are selected in our proposed method and in the multi-commodity mean cost flow approach, which aligns with this requirement of realism to be close to representative trajectories. However, for global mean cost flow, we see that only very small, tiny segments are selected around the checkpoints. And this is also visible in the measures here. And as you can see again, global mean cost flow is best in the deviation, but then in cardinality, our proposed approach performs best. Running time is again, or in this particular case, the mean cost flow where it's best, and realism is more on our proposed methods and the mean cost flow approach, the multi-commodity mean cost flow approach. So in conclusion, what I've shown you today is a way of reconstructing routes from traffic flow. So we propose an iterative method using a Fréchet, modified Fréchet map matcher, and our experiments show that there's this trade-off between realism and deviation. And in future work, we would further model realism, maybe pre-process our representatives, for instance, with central trajectories, and look further into the temporal aspects of the trajectory data and see how we can potentially solve our problem in this particular setting. Thank you for your attention.